Yes, sir. You're audible.
You are audible, sir.
Good. Okay. So let's start the class. So just 1 minute. Just going to chat here. Okay, good. So last class we have started the time domain structure of 5GNR. Okay, just to recap, let's take a couple of minutes to recap. Frame is 10 milliseconds. There are 10 subframes of 1 millisecond each. Each slot has 14 OFDM symbols. Okay, so depending upon the subcarrier spacing, a subframe might have more than one slot. Okay, for example, 15 kilohertz, one slot is equal to one subframe is equal to 1 millisecond. Whereas if you have 30 kilohertz, 2 slots will be there in one subframe, and so on and so forth. Okay, and we have also seen the resource grid. 12 subcarriers form a resource block. Okay, 12 subcarriers form a resource block. That's something that we have to keep in mind. And we also saw the indexing and other things. Okay, so this is where we were yesterday, where we were trying to understand what is the efficiency of OFDM in 5G spectral efficiency. I mean, in terms of efficiency in terms of spectrum usage, not spectral efficiency. Okay, in OFDM. Okay. So, I mean, essentially, I mean, based on the maximum number of PRBs and other things, we can, make it a lot more efficient, depending on the frequency, depending on the bandwidth that's selected. Okay? Good. So today, what we will look at is, today we'll look at a few more things about the resource grid. Then we will look at the FFT sizes, the cyclic prefix sizes. I think by that time, we'll finish up the class, okay?
So how this spectral efficiency is achieved, kind of from 80% to 98%?
Sir, essentially, this is essentially the efficiency of using spectrum. See, in what happens in LTE is in 20 megahertz, they are using only 18 megahertz. They use 1 megahertz on either side as guard bands. Okay, where here what happens is you are using a lot more subcarriers are being allowed to be used for the same bandwidth. That is why it's more efficient. The guard bands, effective guard bands, are more in LTE.
So, but how we are able to manage? We were not able to do that in LTE, but we.
So what they said was essentially the basic idea was, I mean, the transmitters became more complicated. So you have to do some more processing in the transmitter side. So essentially, one thing we learned, Ashok Kumar sir, that OFDM has a slower decay in the frequency domain. Okay, you see more skirts. So effectively, what you can do is either you can do time domain windowing. That's one thing we discussed. Or you actually, people in the base station, they actually do a much more higher order filtering. They just cut off, okay, which causes a little bit of EVM, but they accept it. Essentially, it's a question of how do you implement it rather than a spec.
Okay. But on the device side, also similar kind of efficiency has to be brought. So a lot more complex it will become, right?
Yeah. So on the device side, even in LTE also, they were always using this one. What do you say? Window and app. See, we were using a rectangular window. Because we were using a rectangular window, it was a sync pulse in the frequency domain. The decay was slow. But instead of using a rectangular window, if you use a little bit of more better window in which decays a little bit slowly than falling off suddenly, you can get much more better decay in the frequency domain. Though they use something called window and window overlap and add technique.
Okay. So when we say filtered OFDM,
CPO.
That we deploy
CPO.
Pardon? Acha, CPO. Okay. Right. Thank you.
Okay. So one more thing I want to indicate. So I have also actually added few papers on PAPR and other things in the classroom. Those of you interested can look at that. Okay, there is some interesting papers on PAPR, and I also added some papers on OFDM in general. 2 very good papers on OFDM. Okay, in transactions on communications, IEEE transactions on communication paper. So they deal with both the transmitter and the receiver. Those of you interested, please have a look at them. They're in the classroom.
Okay? So if you can just explain that when we were doing LTE, so we didn't use OFDM as was being used in downlink side. Uplink side, we use SCOFDM, all PAPR issue, right? So we said that because of the PAPR issue, we are not using that, and we are using single carrier OFDM. But in 5G we are using same, downlink, uplink same.
Yes.
How
So,
that PAPR has been managed in
okay. So,
was not, we were not able to manage in LTE. Sorry.
yeah.
So,
What the issue was in LTE, that's the first time OFDM was introduced. Okay. So at that time, only the power amplifiers were coming and other things for LTE. Okay. So, but power amplifiers were mainly designed for GSM and other things, which were single carrier systems, which are very, very efficient. Okay. So in a base station, what you can do is you can do deep digital pre-distortion and other things to reduce the, the side bands and other things, non-linearities and other things. Whereas in a UV side, the linearity of the power amplifier has to be higher, one thing. And second thing also, there is overlap, Windows add and other mechanisms. So when they introduced the LTE, they were not very, very confident that they will be able to do OFDM in the uplink because of these limitations. But as time progressed, there was a lot of developments on the device side, the power amplifiers and the multiple different types of power amplifiers, which are more linear. And they also understood, people also understood how to optimize this for for linearity. So what has happened is, even now, single carrier OFDM has much more better PAPR than CP OFDM. Okay, so the reason why they introduced CP OFDM in the uplink is because it is symmetric. One thing, OFDM is easier than single carrier because you have to do lesser computation than single carrier OFDM. That's one second thing. And the third thing is that the devices have also become much better. Devices have also become much better. Okay, so a combination of all this made them confident that we can do CP OFDM in the uplink. Nothing more than that. There's nothing from a specification perspective.
So is it also related to use a bandwidth part?
No.
The bandwidth part could have been used even in SC or FDMA, right?
SC FDMA also. That has nothing to do with it. And another thing, another important thing that came up is uplink MIMO. See, uplink in MIMO,
This is the main reason. This is the main reason because in uplink also we are using MIMO. So this is very good CPOFDM for that.
Yeah, MIMO plays very well with CPOFDM. Whereas single carrier OFDM and single carrier and the MIMO don't get along well. I mean, you can do MIMO there also, but it's a little bit more difficult. Okay, so these are the reasons why people have chosen CPOFDM. There's also an option of SCFDM in the uplink. Okay. So
there was some discussion on NOMA. So whether NOMA was approved as part of 5G specification or that was dropped?
Not in 15, 17, release 17, the people are looking at it.
Achha, release 17 NOMA may be accepted. Okay, right.
Okay. So before we start, essentially you will see this P cell everywhere in the specification. Essentially, from the course perspective, P cell is nothing but your primary cell. Okay, since we are not going to do carrier aggregation or any other thing, we will only have P cell. Okay, so essentially P cell is the primary frequency, the primary channel in which the UV attaches to the base station. Okay, this is the carrier in which the SSB is transmitted. Okay, that's all we have to understand about primary cell for this moment. Otherwise, the secondary cell and serving cell, this all makes sense when you do carrier aggregation and when you do LTE with non-standalone mode. Okay, for now, let's just focus on P cell. Okay, essentially is the primary frequency in which the UV either performs the initial connection establishment per procedure. Initial connection establishment procedure. Okay, the reason I'm saying is we'll see this P cell everywhere. I just want to tell you what P cell is, primary cell. Okay. So now the question, now we'll start the actual thing. So multiple numerologies are present in NR. Okay, we have 15 kilohertz, we have 30 kilohertz, 120, 60, 120, and 240. Okay. So theoretically, at least as per the specification, different channels can have different subcarrier spacings. Okay, so you can have PDS here, then have one subcarrier spacing. The broadcast channel can have one subcarrier spacing. Of course, whether they implement it or not, that's a different issue. Okay, but at least spec does allow it. Okay, so how do we specify the relative locations of all of this with respect to each other? Okay, so for example, PBCH might have 15 kilohertz and PDSCH can have 30 kilohertz. Okay, how do we make sure that the resource grids of these two, they will have different resource grids now? I mean the resource grids are different because the subcarrier spacing is different. Okay, how do we align these two? What is a common reference coordinate system for all of this in terms of frequency? Okay, So that is what I'm going to try to answer right now. So we require something called a common reference point. Okay, this point is called point A in the specification. Okay, this is not something I'm saying. It is called point A. Okay, so you hear this word point A as if you read the specification, that is nothing but the common reference point. Okay, so let me explain you what this common reference point is. Okay. So I mean, I'm just going to go. I have to go a little bit ahead and do this. So essentially what happens is, first initially when a UV, how does a UV lock onto the base station? A UV locks onto the base station by locking onto the synchronization signals. Okay, in this specific case, the synchronization signals are called SSB. Okay, SSB stands for SS block, synchronization signals block, SSB. So this is something that the base station transmits. Okay, base station transmits this at a certain frequency location. Okay, and the UVs will search across all the frequency locations and lock onto this SSB. Okay, we'll go into very great depth about SSB later, but I just want to give a highlight overview of this. Okay, it will lock onto the SSB. So once it locks onto the SSB, then the base station also transmits something called a SIB1 messages, system information block messages. Okay, so essentially what are the system information blocks? SIB1, MIB and SIB messages, master information block and system information block 1 message. So essentially these are the messages that tell something about the system. Essentially they tell all about the system parameters are there in these messages. Okay, so these messages, in these messages, one thing that the base station informs the UV is, okay, now you have locked onto the SSB. Okay, so once you lock onto the SSB, you know the starting frequency of the SSB. Let me see if I can have a pen here. Okay, just 1 minute. Okay, so this is the SSB. This is the lower part of, this is the first frequency element of the SSB. Okay, so at that point, the UV knows the SSB. UV is locked on, so it knows that location. So what it specifies is there's something called an offset to point A. Okay, offset to point A is given in the SIB1 message. Okay, so once the SSB is locked on, the UV can decode something called as core set 0. The first control information that it decodes is called the core set 0. Okay, so in that core set 0, it will get the MIB and the SIB1 messages. Okay, so once it decodes those messages, it will understand it. One of the messages decodes is called the frequency info downlink SIB. This is the message. This is the IE decodes. And there's multiple things. One of the important things that we require is offset to point A. Okay, this offset to point A tells it from the beginning of the SSB location, where is this reference point A located. Okay, so that's what is specified by that. Once the UV knows point A, it will be able to know exactly where the resource grid is there. Okay, so the resource grid for actual resource grid. So essentially it decodes the core set 0 using, from there it will get MIB and SIB messages. From there it will also be able to decode the point A and the actual resource grid. Okay, so how it's specified is the offset to point A is always specified in terms of 15 kilohertz subcarrier spacing. Even though the grid may be 30 kilohertz, 30 kilohertz or so, 30 kilohertz, 60 kilohertz or whatever, the offset to point A is always specified in 15 kilohertz. Okay, does this make sense? So once the UV is able to understand point A, it knows exactly where the resource grid is. Okay, so that is called as point A.
Yeah, in fact, in the specification for a particular spectrum band and particular subcarrier spacing, from where this SSB will start, that is actually given in the specification.
Given, sir. So when we do the SSB, I will tell you how it is synchronized to the raster and other things. But now what we will do is just I want to understand what is point A. So point A says that once you know the SSB, the lowest subcarrier of SSB relative to point A is the offset to point A. Okay. So how this SSB is transmitted with respect to the raster, we'll do it in detail when we do the SSB. That's the next part of this whole thing. Okay. So that depends on the frequency. So one thing that you should remember is for FR1, 15 kilohertz is the 15 kilohertz uses the basis for offset, and FR2 60 kilohertz. irrespective of what you use for the actual transmission. Okay, does this make sense?
Yeah.
Okay, so as usual, so essentially I put the IE that is there, and I also put the sequence of IE. In SIB1 there's something called serving cell config SIB. In that there's something called downlink config com and SIB. In that there's frequency info downlink SIB, and then that is the offset to pointing. Okay, good. So now let's just talk about a brief introduction to bandwidth part. Again, we'll do this bandwidth part in detail once we finish the MIB and the SIB messages. Okay, for now let's understand what is bandwidth part. So NR, 5G NR supports multiple, I mean, it actually supports very, very wide bandwidth, 100 megahertz for FR1 and 400 megahertz for FR2. Okay. So if you have to do 100 megahertz bandwidth, what is going to happen is, if you have to do 100 megahertz bandwidth, what is going to happen is this one. The DAC and the ADCs have to run at least at 100 megahertz. Okay, so that may be a computationally. I mean, if you buy an expensive phone, maybe it's easy, but otherwise it becomes expensive. The phones might become expensive, and it's also may consume more power. Okay, so suppose you have a phone that can only do 20 megahertz, but it can tune its frequency, but it can only do 20 megahertz bandwidth for processing, for whatever be the reason. Okay, then how do you make it work in the NR kind of situation? Because NR supports 100 megahertz. This is very different from LTE. In LTE, the bandwidth is 20 megahertz and all phones are expected to support 20 megahertz. Okay? Whereas in 5G NR, it's not like that. The base station supports 100 megahertz or whatever is the bandwidth. Okay? It may be larger or smaller. Okay? Whereas the phones need not support entire 100 megahertz. Okay? Because, I mean, supporting 100 megahertz may be expensive in terms of cost as well as processing power. Okay? And that drains out the battery also. Okay? So what will happen is, once the UV locks onto the base station, and once it tells the base, after patch, the base UV tells the base station, hi, I will not be able to support more than 20 megahertz or more than 30 megahertz. Okay, because this is my limitation and I will only be able to support this. Then the base station will say, okay, I will make a bandwidth part for you of 20 megahertz, and these are the multiple bandwidth parts. Okay, so it can ask, the base station can provide multiple bandwidth parts. And the base station will serve the particular UV only in these bandwidth parts. Okay, it does not mean that every slot and the entire bandwidth part is occupied. That depends on the scheduling. But what it says is all the signals, all the channels for that particular UV will be only in that particular bandwidth part. Okay, so this is the bandwidth part of one user. So the bandwidth part of different users can overlap. There's nothing wrong. They overlap generally. Okay. What parts of what resource elements of this bandwidth part are used by every UV in every slot, that depends on the scheduling. Okay, but that's a different issue altogether. So essentially, what is bandwidth part? Bandwidth part is the allowable frequency allowable bandwidth in which the base station serves the UV and the UV transmits to the base station in the uplink. Okay, does that make sense? Any questions?
Sir, the downlink and uplink will be the same frequency?
Yeah, the downlink and the uplink bandwidth part should be in the same bandwidth part. I think so. Of course, unless it's an FDD system. In FDD system, of course, there will be different parts. Okay, in TDD system, they will be the same bandwidth part. I think so. But I'll confirm that when we do the bandwidth part. I'll confirm that question.
Okay.
So it is actually the same, sir, because for example, for IoT devices supporting a very limited bandwidth part to save the power and all, so it has to be the same uplink and downlink, whatever UV supports.
Yeah, I think so, but I just wanted to confirm because they write it separately. But we will anyway, when we do the bandwidth part, the signaling of bandwidth part, we'll understand this carefully. But what you said makes sense, sir. Because I also assume that uplink and downlink should be in at least in TDD system should be in the same bandwidth part. In FDD, of course, they are anyway different. They're in different frequencies altogether.
But in FDD also, so when we say bandwidth part 1, that will be defined. What is the uplink and what is the downlink frequency for that part 1?
Yes.
And in TDD, of course, it has to be same, right?
Has to be same. But let's just confirm it when we do the bandwidth part in detail. Okay. See, what I want to understand, what I want you to understand from this part is that in NR, you can have UVs which don't have to serve all the 100 megahertz. Okay, even if you have 100 megahertz bandwidth by the base station, you can have UVs which can support 5 megahertz, 10 megahertz, and so on and so forth. There are restrictions to that. We'll again understand that. But essentially, what we have to understand is that lower bandwidths are allowed. Okay, so bandwidth parts is not the scheduling. Scheduling is very different from bandwidth parts. Okay, you have to understand this distinction. So, for example, your bandwidth part may be 10 megahertz. That doesn't mean every time the base station serves you, it always allocates you 10 megahertz. Okay, so base station will always serve you in the 10 megahertz. It may serve you with lower bandwidth. It can serve you with 1 megahertz. It can serve you with 50 kilo. I mean, whatever, some 60 kilohertz also. Mr. Srivatsava, please.
Yeah, in DL or UL, UV can have 4 bandwidth part.
Yes,
so, bandwidth part is actually some part of the bandwidth that is allotted to UV in which it can transmit or receive.
Yes, that's
so
all.
4 bandwidth part means what? But how you are means there can be 4 different kind of band which can be carrier aggregated like that?
No, sir. Essentially, what happens is at this particular time instant, I will serve you in bandwidth part 1. Okay, after some time, you can serve in bandwidth part 2.
Again, at the same time, it cannot be in 4 bandwidth.
No. At a single time, only 1 bandwidth part is active.
Okay.
So example of this Manoranjan is like when there is less data transmission, it can use a bandwidth part which has low bandwidth. And suppose suddenly you start doing video and all, so so the second bandwidth part it can use, right? So it's for power saving, or your devices will be more power efficient on LTE. In LTE, we used to use the entire 20 megahertz band onto the devices side, where in 5G, we are more particular about power saving and also, so that will take care of.
But sir, this is about something like power control only. That was in other specifications also, 3G, 4G.
No, sir.
That power control.
No, that is different. Power control is totally different. That is a radiated power. This is the bandwidth.
So essentially, what happens if you have this? Suppose
actually, it is dynamically allocating the bandwidth as per the requirement.
Bandwidth as per requirement. But
sir, let me explain this. So essentially, suppose you have bandwidth part 1. Okay. So what does this bandwidth part 1 means? Whatever signaling that the base station is transmitting to the UV has to be in this bandwidth part 1. And whatever signaling or control information that the UV is transmitting to base station has to be in this bandwidth part 1. Okay, similarly for bandwidth part 2. Suppose, so essentially, even if you are not getting any data, the UV has to make sure that it is, listening to this entire bandwidth part 1. Okay. Similarly, if it is active in the bandwidth part 2, it has to listen to the entire bandwidth part 2, even if it's idle. Okay, so that will take more power and more thing from its ADCs, DACs, and other things. So if the UV knows that, okay, I don't want this much bandwidth at all. I want only 10 megahertz. I don't want 20 megahertz. Then it can tell the base station that I will only do 10 megahertz bandwidth part 1 now. So in this 10 megahertz, the base station can allocate any band in this 10 megahertz. It can allocate 1 megahertz, it can allocate 5 megahertz. That depends on the scheduling. That depends on the number of users and scheduling. Okay. So in that way, it will also save its battery and power and computation resources, because it doesn't have to even if it is in ideal mode, it doesn't have to scan this entire bandwidth part. Okay.
And just to add for IoT kind of devices, they may not be required to actually support all the 4 bandwidth part. It may only support, say, bandwidth part 1. And there will be devices which can support all the 4 bandwidth part. I mean, suppose it is having 100 megahertz, then it can have multiple.
So whether these bandwidth parts are predefined or pre-assigned to you, sir?
Yeah, you are right. So bandwidth part, yes, there are type of devices. One is that so every device will have radio capability ID, and that radio capability ID also gives which bandwidth part it has actually the capability. What is actually the design, and other is called network allocated kind of capability ID. So network can also allocate, and device can also have limitations. So both is possible in 5G.
So,
Okay.
If you want to
so
add.
what happens is there'll be negotiation between the base station and the UE. Okay, and they come up to one common bandwidth part. So we will do that. We will come to that when we finish. So essentially, we do it step by step. First, let's do the synchronization. Once they do synchronization, then we go into what are the messages that are exchanged for this bandwidth parts. Okay, that time it will become clear. Okay? The reason I'm saying this bandwidth part is because for the next slide I require this.
Sir, suppose that base station 100 megahertz bandwidth is available, but UE has the limitation of only 20 megahertz. Then how this 100 megahertz is utilized, or only it will work on only that 20 megahertz?
Okay. So essentially the 20, so suppose, let me just redraw this figure. So suppose the UE says I can only do 20 megahertz, but it cannot say I can do only 20 megahertz in this particular frequency. It's not allowed. It can do, so the base station can allocate the 20 megahertz anywhere in this carrier of 100 megahertz. Okay. So what will happen? The other UEs may support the 100 megahertz bandwidth part. Okay. The other UE, for example, the other UE. Okay. So this may I'll just put in different color. The other UE bandwidth part one might be like this.
Okay.
Okay. The third UE, I mean, there were so many UEs, no? They may cover the entire thing. The UE, it's okay. Just put it here. Fine. Does it make sense, Mr. Chitranjan?
Sir.
Okay. Good. Okay. So there is something called as common resource blocks and physical resource blocks. Okay. So what are common resource blocks? So common resource blocks are for the base station. Okay. So essentially they are from the point A absolute reference. You have a resource block with a certain subcarrier spacing that goes 0, 1, 2, 3. And these are the resource block. This is a common resource block number. It always starts with the point A. Okay. And physical resource blocks are for that particular bandwidth part for that particular UE. Okay. So physical resource, So for example, in this particular case, this is the bandwidth part that the UE got. Okay. So his physical resource blocks start at, okay, let me show my laser pointer. Okay. So his resource blocks start at this point. Okay. So that starts at 0, 1, 2, 3, 4, 5, and so on. Okay. So physical resource blocks are with respect to a particular bandwidth part, whereas common resource blocks are with respect to the absolute reference. Okay. The absolute reference starting point is the common reference block 0. Does it make sense? Yes. So you can go from NCRB. It is called NCRB, number CRB, number PRB. Okay, the numbering. So you can go from common reference block to physical reference block by just adding the starting point of the bandwidth part. Okay, so you will see both of them in the whole specification. One is the common PRB and one is called the CRB. So when PRB means PRB is always referenced with respect to the starting point of the bandwidth part, whereas common resource blocks are always referenced with respect to point A. Please, you have to keep this in mind always. Okay. That's the reason why I introduced what a bandwidth part is. Okay. So different bandwidth parts have, so a bandwidth part, one user will have 0, 1, 2, 3 from here. Other user can start it here, and it is 0, 4, 1, 2, 3, 4, 5 will start from this point. Fine. So in the specification, when we specify DMRS and other things, they will tell you whether it's with respect to CRB or whether with respect to PRB. Okay. So SSB and other things will be with respect to one something, and the DMRS and other things will be with respect to something else. So we should be very clear in identifying them. Okay. Good. Any questions before we proceed? So now let's get back to understanding what is the cyclic prefix sizes, what is the FFT sizes and other things. Okay, I think this is something that we have some discussion yesterday also. Okay, so I'm going to just exit from full screen because maybe we have, okay. So let's see this. So first of all, I want to understand how I choose my FFT size and how I choose my sampling. Okay, let's take the example of 30 kilohertz subcarrier spacing, and you have 100 megahertz bandwidth. Fine. So 100 megahertz bandwidth, 30 kilohertz subcarrier spacing means, first of all, I have to go here and see in this table 100 megahertz You see my cursor now, and 30 kilohertz subcarrier spacing corresponds to the maximum of 273 PRB. Okay. So when you have 273 PRB, so each PRB has how many subcarriers? 12 subcarriers. So 273 into 12 is equal to 3276 subcarriers. Okay. So you have 3276 subcarriers. So you have to do an FFTs. FFT. Okay. So generally what happens? FFTs are generally of power of 2. Okay. So what is the power of 2 here implies? What is the closest power of 2? That will be 4096.
4096.
Okay. So therefore, what will happen? So therefore we choose 4096 FFT size. Okay. So now you have what is when you choose 4096 FFT size, what is your N? N is 4096. So what will your sampling rate be? Your sampling rate will be 1 by 4096 into 1 by N into delta F. 1 by 4096 into delta F. That will be your sampling time. And you can see that this is nothing but 16 times TC. Okay, because TC was 1 by 4096 into 480 E3. So this is exactly 16 times TC. Okay. So recall that 64 TC corresponds to 30.72 megasamples per second. We saw that yesterday. This is exactly LTE. 64 TC is 30.72. If 64 TC is 30.72, okay, I mean 64 TC means 1 by 64 TC is equal to 30.72. 1 by 16 TC, which is the sampling frequency, will be 4 times 30.72. So you'll do 122.88 megasamples per second. Okay. So what does this mean? So this means that when you have 100 megahertz bandwidth, okay, when you have 100 megahertz bandwidth, we are sampling at 122.88 megasamples per second. Okay, when 30 kilohertz subcarrier. If you do the same computation for 30 kilohertz subcarrier spacing and 50 megahertz bandwidth, again, for 50 megahertz bandwidth, you will do 30 kilohertz is 133 subcarriers maximum. Okay, so 133 into 12 is 1596. So you can use in the closest FFT size is 2048. Okay, so therefore the sampling time is 1 by 2048 into 30 E3, which is 32 TC. So this is 61.44 MSPS. Okay, so let us look at the millimeter wave system. So we have 400 megahertz bandwidth and 120 kilohertz SCS. 400 megahertz bandwidth and 120 kilohertz SCS is 264 PRBs. Okay, so 264 into 112 is 3168, and the closest FFT size is 4096 FFT. Okay, so if you find the sampling time is 1 by 4096 into 120 E3, which is 4 times TC. Okay, so when you have 4 times TC, it is 491.52 megasamples per second. Mr. Srivatsava, please. Hello, sir.
When we are deriving the number of resource blocks required, can we not directly divide it? If we divide it 50 by 30 kilohertz, 50 megahertz by 30 kilohertz, it will come 1600 something it will come. So why less number of subcarriers it appears in the table?
You are saying that instead of 3276 by 2 is not 1596, it's some 1600 something, huh?
Yeah. I mean 50 megahertz divided by 30 kilohertz, if I do, the number of resource blocks should come, no? About. So
the way they chose this table,
the number, that is the gap. There is some numbers which is derived by division and this.
Yeah, so if you look
what is the region of the gap?
Yeah, so I'll tell you, sir. If you look at this table, 273 and 133. 273 by 2 is not 133. It's little less. It's about 6 subcarriers less, 5 subcarriers less. 5 subcarriers less.
Yes, sir.
So the reason is, this table is decided by the RF people. Okay, so 38101 series is the RF people. This is decided by RAN4. When they decided the RAN4 things, what they saw was, so essentially, they chose the number of subcarriers so that the ACLR spec and other things are.
Actually, this is transmission bandwidth. You just see on the top of the table, this is transmission bandwidth. So this is decided by the RF people considering adjacent channel ratio and on many things.
So, I mean, they made sure that they gave some more gap, so that the ACLR specifications and other things are met. That is the reason why these numbers do not. So 100 to 450 and 225 is not exactly one half and 1/4. Okay, it's something else. So what they did was they did some simulations and other things and found out that if you use 133, you will meet the spec. But if you put 170, 135 or 136, you are a little difficult to meet that specification. Okay, that is the reason why they chose that.
So sir, there is a table where it gives for particular bandwidth how much guard band both sides is required, and then if you divide by 15 kilohertz or 30 kilohertz, these exact numbers are coming actually.
Yes. So there's a guard band also. The guard band. So this difference will be compensated by the guard band, of course. That's true. Rajavardhan, you raise your hand. Rajavardhan? Oh, you don't have a mic. Okay. Okay, fine. Sorry. Okay.
Excuse me, sir.
Yeah, please.
Sir, can we test this in the MATLAB? Sir, can we change these 133 to 135 different subcarriers and we can observe the result?
The ACLR and other things. Hello.
Yes, sir. Here we are talking about 133, sir, 50 megahertz and 30 SCS.
Okay.
So if we change it to 130, and what are the changes we'll observe in respect of speed or other things? Can we test in the MATLAB, sir?
And actually, once we write the whole thing, we can do that. We can understand that. It's perfectly, I mean, we can do that. We can even do the ACLR. We can do all those things in MATLAB. Okay. We'll slowly start developing those things. I mean, in this semester, we will do that. Okay. So there's one thing I wanted to show you. Just give me 1 minute. Okay, so this is a picture I wanted to show you. Okay, so let me ask you this question. So we are using, so essentially if you look at 4096 into 30E3, let's do what is the bandwidth that you get. 4096 into 30E3. That's 122.88 megahertz. Okay. So all the subcarriers use about 122.88 megahertz bandwidth. Okay, but you are allocated only 100 megahertz bandwidth. Okay, so what happens actually? Okay, you are allocated only 3276. 3276 subcarriers into 30 is 98 megahertz is allocated to you. Okay, so what happens is, that's why I wanted to show you this picture. So this was something that I have done for LTE. So LTE, what happens? I mean, you can use this. We can also do this. Okay, so the maximum number of subcarriers is 1200. Okay, so subcarrier spacing is 15 kilohertz. So 18 megahertz is what you can use. So we choose 1200, the closest option is 2048 FFT size. Okay, so 2048 in 1500 is 30.72. This 30.72 corresponds to 2048 subcarriers. Okay, out of this, the useful subcarriers are only 1200. Okay, so we approximately leave about 800 subcarriers. 800 subcarriers are actually not populated. Okay, and of course, there's 1 megahertz guard band on both sides. So your FFT size is much more than your entire bandwidth that's allocated to you. You're allocated only 100 megahertz, or in this case only 18 megahertz or 20 megahertz bandwidth, but your FFT size is over 30.72 megahertz bandwidth.
Sir, then in this case, then information loss of information not happen because your FFT size is more than the usable bandwidth.
Yeah, but sir, you're going to put zeros here. So in all this subcarriers and this subcarriers, you're going to put zeros.
Okay.
Okay. So the same thing we'll do it with 5G NR. Just let's understand this, because this is what confuses people in implementation.
Sir, is it not a inefficient design?
No. This is actually very good design. Let me explain you this properly. Okay. See, we got 100 megahertz bandwidth. Okay, this is my bandwidth. 100 megahertz is allocated to me. Okay. And 30 kilohertz subcarrier spacing. So we saw that our N is equal to 4096. Okay. And 4096 into 30 will be what? 122.88 megahertz. Okay. So I'm just going to put both sides. So 122.88 is this. Okay. So technically, if I do 122.8 megahertz, this thing FFT, I mean the 4096 FFT with this, I'll be able to decode anything in this bandwidth. Okay, so essentially how are my subcarriers? My subcarriers are like this. Okay, I'll be able to decode anything. But what I'm going to do is, I am going to put zeros most of, so in our case, how many useful subcarriers are there? Just let me just one minute see. 3276. So 3276 by 2 is how much? 1600 30. How much is this? 3276 by 2. 1638. Yes. Okay. So what I'm going to do is I'm going to use 1638 subcarriers here. I'm going to use 1638 subcarriers here. Okay. And all the others I'm going to put this, of course, guard band. I'm not putting the guard band. All the other things I'm going to put zeros. Okay. So effectively, how does the spectrum look when I transmit this on a spectrum analyzer? If I transmit this on a spectrum analyzer, how does the spectrum look? Because I put zeros here in this subcarrier and take an FFT and transmit, my spectrum will look like this. Okay. So effectively, I'll get only 100 megahertz spectrum. Or whatever, plus or minus those guard bands. Okay. That way I am not putting here. So this FFT size is 4096. Does it make sense?
Yes.
Okay. So you see,
this will also serve the purpose of that decaying of that your OFDM signal also.
Yes, precisely. So what happens is, I'll also put the guard bands actually. We can also check how much is the guard band duration. Let's just do that exercise once. So it says 30 kilohertz. Minimum guard band and transmission bandwidth configuration. Okay, so it's about 845 kilohertz. I don't know which is on the both sides or one side. It's on both sides. Okay, 845 kilohertz. So 845 kilohertz at 30 megahertz is approximately about 30 subcarriers. Approximately about 28 subcarriers or so. So 28 subcarriers here are guard bands. Okay. So what will happen is when your actual signal will be, I will just draw this properly. I'm just putting approximate numbers. You have to do this computation properly.
Your pad is not visible.
Sorry. Okay. So there are 28 subcarriers which are zeros. Okay. So these are the guard bands. I'll just draw this like guard bands. Okay. So what will happen is this will not be 100 megahertz. This will be some 90 whatever. How much did we compute this? 98 point something. Okay, some 98 megahertz will be there. 1 megahertz guard band here. 1 megahertz guard band here. Okay, so in this 1 megahertz, this roll off will be there. Okay, Pandey sir, that explains this thing now.
Everywhere in LTE and 5G also both, the transmission bandwidth is always less than the channel bandwidth, just to have the proper signal. That is the thumb rule.
Yeah, because you want to get the decay. So
yes,
in LTE it was more. Now in 5G it's a little bit less. That's all. Okay. But the most important thing I want to understand is 4096 FFT does not correspond to 100 megahertz. It corresponds to 122.88 megahertz.
Yes,
okay?
yes. Certain.
So what you should do is, so after you take your FFT, you should drop all this. You should drop all the zeros. A lot of this will be zeros. You just drop them off and just extract whatever is the actual resource blocks that you have. Fine, that makes sense.
But sir, in actual transmission, that 122.88 out of that 100 we have used, and the remaining 22.88 megahertz will go just like that, and it is the wastage of the bandwidth or what?
No, sir, nothing will be there inside that. It's zero.
Nothing is there, but it will not get transmitted.
It's putting like zeros is, you are transmitting at 122.88, but there is no information there. So effectively, signal will be zero in that.
But it is being transmitted, so we are wasting the resources there.
Wasting what? You're wasting your energy. I agree. Wasting your energy and complexity. That I agree. That I totally agree. But from a spectrum perspective, you're not wasting anything.
For a spectral perspective, we are not wasting. Okay.
But I agree with that you are sampling it at a higher rate than necessary. Technically,
Yes.
I can sample at 90.98 megahertz sampling rate. Okay.
Sir, but we cannot use this particularly 22.88 megahertz for some other purpose also.
No, you cannot.
Yes.
Yeah. So what
that PAPR may increase, sir?
So PAPR has nothing to do with this because
nothing is with PAPR here.
Nothing with PAPR actually. See, one thing is, sir, Pandey sir, one other thing that I have to tell you is, see, if you do 3096, 99.88, then your FFT size has to be different. It has to be 3276, which is not a good FFT size. Okay, so it's better to do 4096 FFT and remove all the zeros in front and back.
Definitely, we have to do in the power of 2, that FFT and IFT.
Yeah, that is a big constraint.
Yes.
Okay, so please keep this in mind. So the sampling rate is always higher than your bandwidth because of this FFT size.
Excuse me, sir, one basic question.
Mr. Vijay, please.
Sir, for example, DOT allocates 100 megahertz to one of the TSPs, sir.
Yes, sir.
So how he can go to 122, sir, because of this?
So, sir, Mr. Vijay, let me just again explain you this. Okay. So let's take one more page. Let's. Okay. So DOT, what does it allocate? Allocated 100 megahertz. I'm just going to draw a square of 100 megahertz. Okay, so this is my allocated bandwidth. Okay.
Sir, you can also draw another 100 megahertz given to other operator just beside this, so that you are able to.
So maybe you just draw. You will just give one more guy.
Just beside this, keeping very small. Yes, you're right.
Yeah, 100 megahertz. Okay. So what is going to happen is, I'm just going to draw the other side.
So the question is that it will be overlap of the FFT size.
Yes. Overlap.
How those are managed? That's the question, perhaps.
That's the question. Yeah, exactly. Let me explain you that. So 122.88 by half is about 61.4. Yeah, 61.4. Okay. So your FFT size will be like this. Yes. This is your 4096 subcarriers. Okay, this bandwidth is 122.88 megasamples per sample. Fine. So what are you going to do? Your DAC, your ADC is going to operate at this frequency, or your DAC is going to operate at this frequency. Okay. But let us look at what are the what are you putting in terms of subcarriers. Okay, so there are 4096 subcarriers corresponding to this point to this point. Okay, what you do is what you effectively do is, there are lots of subcarriers here. In all these subcarriers here, you put zeros. First, let's talk about transmission. You always put zeros. Okay, a few more zeros here because of the guard band. Okay, and then your actual data will be in these subcarriers. Okay, 3276 subcarriers. Okay, so effectively, how will your spectrum look if you draw the spectrum? Because you're putting zeros here, nothing is going to come out in that frequency bands. So your effective spectrum will look like this. It is still 100 megahertz, 100 or little bit less than 100 megahertz. Okay, so on the reception side, what do you do? Okay, on the reception side, you are going to get junk from this guy. You're going to get junk from you're going to get junk from this guy. You're going to get junk from this guy. Okay, so you are going to take an FFT of whatever 4096. Okay, then what are you going to do? You know that your subcarriers are only 3276. You discard all these subcarriers, these edge subcarriers, and you just consider only 3276 subcarriers. Yes, you discard them. Therefore, there's no interference from here to here. There's no interference from here to here. Okay?
Sir, can I ask the follow-up questions?
Yes, please.
Sir, how this will be implemented in the TSP systems? For example, DOT has allocated 100 megahertz from 700 series. If you take 700 to 700.1, for example. 700 megahertz means 700 to 800 they will give, sir.
Yes, sir. 700 to 800. Okay.
800. Now in the TSP system, if I check the backend system, so they will start from 122 means some around 690. If they start 690 to 810, they will show, it will be reflected in their system, sir.
No. It will still reflect from, I'll take the center frequency as 700. So this will be 650 and this will be 750.
Yes, sir.
So only this part, this user, this particular, for example, this is operator 1. O1 does not transmit or receive anything outside O1. It will receive something from outside, but that is not an interference to you because you can drop them.
No, sir, but over the air transmission, sir, over the air transmission.
Over the air transmission, see, this is the over the air transmission. This is exactly the over the air transmission, no? When you're transmitting
zeros, but whether the data is there or not, zeros are also being transmitted, sir.
Zeros means nothing. Zeros means nothing. It won't affect your spectrum. Zeros means nothing. There's no power in those carriers. Zero means actual zero value. So there's no power in that spectrum, in those frequency bands, in those frequency bins.
Yes, sir.
So I think in effect 122 megahertz is only for when we do FFT and IFFT receiver side, whatever do you at that point of time we process that bandwidth just to, and also discard that, because we cannot use other than 2048 or 4096 FFT or IFFT. So it is just for the processing purpose. As far as signals, physical signals are concerned, those are not there at all. Other than megahertz, yes. So it is just for processing, and while processing, you discard those which is coming 11 megahertz this side and 11 megahertz other side. I hope this is the case, right?
That's correct, exactly correct, sir. See, technically, if you had a very efficient FFT at 3276, I will not even do all this. Okay, I will just do a 3276 FFT. But 3276 FFTs are not there now. I mean, it's not effective. You can do it, but it's not effective. So what you do is you sample it at 122.88, get a larger bandwidth, but discard all the side things effectively. Okay?
Yes, sir, it is okay.
Okay. So, okay, I think it's already 9:54. We'll stop at this point. Next class, I want to teach you about the cyclic prefix, and I will also look at how are the cyclic prefixes for different symbols and other things. Okay. Thanks, everyone. Thank you.
Thank you.
Thank you, sir.